The universe holds secrets so bizarre they defy everything we think we know. Picture a cosmic drain, a black hole, sucking in everything around it, light, time, even reality itself. Now imagine its opposite, a cosmic fountain erupting with energy and matter from nowhere. This isn't science fiction. White holes, the mysterious twins of black holes, might be real, and what we've uncovered about them will bend your mind. For decades, white holes existed only in equations, dismissed as mathematical oddities. But today, cutting-edge theories suggest they could be the key to understanding the Big Bang, wormholes, even the fate of the universe itself. Some scientists believe these enigmatic objects could be black holes running backward in time. Others think they might be gateways to other dimensions. And then there's the chilling possibility: what if we've already detected them without realizing it? In this video, we're diving into 25 of the strangest, most mind-blowing discoveries about white holes. From their eerie connection to dark matter to the terrifying idea that they might defy the laws of physics, each revelation will leave you questioning the nature of reality. Could a white hole have birthed our universe? Is there one lurking in the depths of space right now? Stay with us, because by the end, you'll see the cosmos in a way you never thought possible. Let's begin. Now, let's peel back the layers of our first strange discovery. Picture a black hole in reverse. Instead of pulling everything in, it pushes everything out. That's the wild idea behind white holes as theoretical time reversals of black holes. Imagine hitting rewind on a black hole's life. What you'd see is a white hole spewing out all the matter and energy the black hole once swallowed. This isn't just a sci-fi twist. It's a real possibility rooted in Einstein's field equations, the same math that predicted black holes in the first place. Einstein's equations don't care which way time flows. They work just as well backward as forward, and that's why physicists take this idea seriously. A white hole could be a black hole's mirror image in time, a place where the universe's most destructive force becomes its most creative. The math even suggests that if you could somehow flip a black hole's timeline, you'd get a white hole, a cosmic reset button. But here's where it gets even stranger. If white holes are real, they'd challenge our understanding of cause and effect. Normally, events happen in order: first the cause, then the effect. But with white holes, that sequence could flip. What if the eruption of matter from a white hole today was actually the result of something a black hole will do in the future? It's a dizzying thought, one that makes physicists both excited and deeply uneasy. And that's just the beginning. The idea of time-reversed black holes opens doors to even weirder possibilities, like whether white holes could be gateways to other universes or even the remnants of a previous cosmic cycle. But we'll save those brain melters for later discoveries. For now, let this sink in: white holes might not just be cosmic oddities. They could be black holes playing the universe's greatest magic trick, running time backward. Now, let's turn our attention to something that makes white holes even more baffling: their apparent defiance of one of the universe's most unbreakable rules. The second law of thermodynamics tells us that entropy, or disorder, always increases over time. It's why your room doesn't clean itself and why heat flows from hot to cold, never the other way around. But white holes, they seem to laugh in the face of this law. Think about it. A black hole obeys the rules perfectly. It swallows matter and energy, increasing entropy as everything gets crushed into chaos. But a white hole does the opposite. It spits out matter and energy without any obvious source, like a cosmic fountain that never runs dry. If entropy is the universe's way of keeping things messy, white holes are the rebels making everything neat again, and that's a problem. Scientists are torn over this. Some argue that white holes can't exist precisely because they break this fundamental law. Others suggest there might be a loophole. Perhaps the energy white holes eject comes from somewhere we can't see, like quantum fluctuations or hidden dimensions. Then there's the wildest idea of all, that white holes don't violate the second law but instead balance it out across time. If a black hole's entropy increase is offset by a white hole's decrease elsewhere, the universe's books might still balance in the end. This debate isn't just academic. If white holes really can bend the rules of entropy, it could rewrite our understanding of how the universe ages, how energy flows, and even whether time itself has a direction. For now, though, the mystery remains. White holes stand as cosmic rule breakers, challenging us to rethink what we know about order, chaos, and the laws that hold reality together. And if that's not mind-bending enough, wait until we explore how white holes might be tied to the very birth of the universe itself. But that's a story for the next discovery. Now, let's take a cosmic leap back in time, because what if white holes aren't just strange anomalies, but the very seeds of existence itself? Some cosmologists have floated a radical idea that our universe might have been born from a white hole. Think of it like this: if a black hole is a one-way door into oblivion, a white hole could be the exit, a burst of energy and matter erupting into a new reality. This ties into something called the Big Bounce hypothesis. Instead of the universe starting from a singular point of infinite density, the classic Big Bang, this theory suggests our cosmos might be part of an endless cycle. A previous universe collapses into a black hole, which then rebounds as a white hole, birthing a new universe in the process. It's like the cosmic version of a phoenix rising from its own ashes. The implications are staggering. If white holes played a role in creation, they could explain why our universe seems so finely tuned for life. The energy and laws we take for granted might have been forged in the white hole's explosive genesis. But here's the catch: this idea is still on the fringes of physics. For one, we'd need evidence of a universe before ours, and right now, that's like trying to find footprints in a sandstorm. Yet the possibility lingers. If white holes are cosmic rebirth engines, they'd rewrite not just our origin story, but our destiny. Maybe the Big Bang wasn't the beginning, just a turning point in an eternal cycle of collapse and renewal. And if that's true, the white holes we're theorizing about today might one day become the creators of universes we'll never see. Speaking of creation, our next discovery takes us even deeper into the unknown, where white holes might be behind some of the most violent explosions in the cosmos. But more on that in a moment. Now, let's turn our attention to the skies, because some of the most violent and mysterious explosions in the cosmos might just be the fingerprints of white holes. Picture this: a burst of energy so powerful it outshines entire galaxies for a fleeting moment. These are gamma-ray bursts, some of the most energetic events in the universe, and their origins remain one of astrophysics' greatest puzzles. But here's where things get intriguing. A handful of scientists have proposed that these outbursts could be the work of white holes. Think about it. If a white hole is spewing out matter and energy in a sudden, explosive event, it would match the profile of these cosmic fireworks. One particularly baffling example is GRB 060614, a gamma-ray burst detected in 2006. It lasted just a fraction of a second, but packed more energy than our sun will emit in its entire lifetime. Traditional explanations like collapsing stars or merging neutron stars struggle to account for its sheer intensity and bizarre afterglow. Then there's the case of fast radio bursts, bright pulses of radio waves from deep space. Some of these signals repeat while others vanish without a trace. Could these be white holes flickering into existence and vanishing just as quickly? The idea isn't as far-fetched as it sounds. White holes, by their very nature, would be fleeting, erupting with energy before closing up shop. Of course, not everyone's convinced. Critics argue that these events could still be explained by known phenomena, like magnetars or black hole jets. But here's the kicker: some gamma-ray bursts and fast radio bursts come with odd quirks, unexpected energy distributions, strange timing, or locations where no obvious cosmic culprits exist. These anomalies keep the white hole hypothesis alive, dangling the tantalizing possibility that we're witnessing the last gasps of these theoretical objects. So, what's the verdict? For now, these outbursts remain cosmic riddles. But if future telescopes catch a burst that defies all conventional explanations, we might just have our first glimpse of a white hole in action. And speaking of action, our next discovery takes us into the realm of interstellar shortcuts where white holes might be the key to unlocking the universe's hidden highways. Now, let's take a leap into the realm of science fiction turned potential reality. Imagine a cosmic tunnel connecting two distant points in space, a shortcut through the universe. This is the idea behind wormholes, and white holes might just hold the key to making them real. According to Einstein's theory of general relativity, a wormhole, or Einstein-Rosen bridge, could theoretically link a black hole in one region of space to a white hole in another. Picture it like a one-way street. Matter gets sucked into the black hole, and then poof, it's ejected out the white hole on the other side. This wild concept suggests that white holes could be the exit doors of these interstellar tunnels, offering a way to traverse vast distances in the blink of an eye. But before you start packing your bags for a trip across the galaxy, there's a catch. Wormholes, as far as we know, are incredibly unstable. The moment they form, they'd likely collapse under their own gravity unless propped open by some exotic form of matter with negative energy, something we've yet to discover. Even if they stayed open, the journey through one would be anything but smooth. The intense gravitational forces near a black hole's singularity would stretch and squeeze anything passing through in a process scientists call spaghettification. Not exactly a pleasant travel experience. Still, the idea has captured imaginations for decades, especially in science fiction. Films like Interstellar brought wormholes to life, depicting them as shimmering portals bridging distant star systems. While the movie took creative liberties, it wasn't entirely off base. The science behind it was vetted by real physicists. So, could white holes really be the gateways to interstellar travel? For now, it's a thrilling possibility wrapped in layers of theoretical physics. But if future breakthroughs uncover stable wormholes or exotic matter, we might one day look to white holes as the universe's ultimate express lanes. And speaking of cosmic mysteries, our next discovery dives into a paradox that makes white holes even more baffling: why you can never step inside one. Now here's something that twists the mind even further. While black holes are cosmic vacuum cleaners pulling everything in with no escape, white holes flip the script entirely. Picture a cosmic fountain. Water gushes out, but you can't jump back in. That's the essence of the never-enter paradox. By their very nature, white holes forbid entry from the outside. They're exit-only doors in the universe, spewing out matter and energy but slamming shut to anyone or anything trying to get in. Think about what that means for an observer. If you stumbled upon a white hole, you'd witness a spectacle of particles and light bursting forth. But no matter how close you drifted, you'd never cross its threshold. It's the opposite of a black hole's event horizon, which lets you in but never out. This bizarre property makes white holes more like cosmic mirages, visible yet utterly untouchable. Why does this matter? It challenges our understanding of physics. Black holes obey the rules we know, even if they stretch them to extremes, but white holes, they seem to break the playbook entirely. If nothing can enter, how do they even exist? Some theories suggest they're remnants of black holes that have undergone quantum transformations, while others argue they're purely mathematical oddities with no physical form. One thing's for sure, the never-enter paradox forces us to rethink how space, time, and causality interact. And as we peel back these layers, the next discovery dives even deeper into the quantum realm, where white holes might not just defy gravity but rewrite it entirely. Now let's venture into the quantum realm, where the rules of gravity get a radical rewrite. Here's where things get even wilder. White holes might not just be theoretical oddities but could actually form from the chaotic collapse of a black hole, thanks to the bizarre effects of quantum gravity. Picture this: as a black hole reaches the end of its life, instead of vanishing into oblivion, quantum mechanics steps in and flips the script. The intense gravitational collapse could hit a wall, a quantum bounce where the crushing forces reverse, and the black hole transforms into a white hole. It's like a cosmic phoenix reborn from its own ashes. This idea comes from loop quantum gravity, a framework that tries to bridge Einstein's relativity with quantum mechanics. Physicist Carlo Rovelli and others suggest that at the tiniest scales, space isn't smooth but made of woven loops. These loops could prevent a black hole from collapsing into an infinitely dense point, instead triggering a rebound, a white hole eruption. What's fascinating is the timescale. While this transformation might seem instantaneous to an outside observer, for the black hole itself, it could take billions of years due to time dilation. That means the white holes we imagine might be ancient black holes finally bursting back into existence. This theory isn't just science fiction. It's a serious attempt to solve the black hole information paradox and redefine how we understand space-time. And if quantum gravity holds the key, white holes might be more than just mathematical curiosities. They could be the universe's way of hitting the reset button. Up next, we'll explore an even more controversial idea. What if these elusive white holes are hiding in plain sight, masquerading as something else entirely? Now, let's take a sharp turn into one of the most debated corners of cosmology. Could white holes actually be hiding in the shadows of the universe as dark matter? It's a bold idea, but some scientists think these cosmic enigmas might explain one of the biggest mysteries in physics. Here's the puzzle. Dark matter makes up roughly 25% of the universe's mass, yet we've never directly detected it. We only know it's there because of its gravitational pull on galaxies. So what if some of that invisible mass isn't made of exotic particles, but of ancient white holes left over from the early universe? Primordial white holes, hypothetical relics from the Big Bang, could fit the bill. Unlike black holes, they wouldn't swallow light, but they'd still warp space-time with their gravity. If they exist, they'd be faint, nearly impossible to spot, and scattered across the cosmos just like dark matter. Some researchers suggest these white holes could be the missing pieces, lurking unseen while shaping the universe's structure. But skepticism runs deep. For one, white holes are already speculative, and linking them to dark matter piles theory on top of theory. Plus, dark matter seems to be smoothly distributed, while white holes would be point-like, creating clumps of gravity that don't quite match observations. And then there's the energy problem. White holes spew out matter and radiation, which doesn't align with dark matter's silent, ghostly behavior. Still, the idea isn't completely dismissed. If white holes formed in the chaos of the early universe, they might have unique properties we haven't imagined yet. Maybe they're colder, quieter, or clustered in ways that mimic dark matter's effects. Until we have better telescopes or new physics, it remains a tantalizing what-if one that keeps scientists debating and digging deeper. Coming up, we'll tackle another mind-bending question: what happens when a white hole meets the laws of thermodynamics head-on? Now, shifting our gaze to another fascinating puzzle, let's explore how white holes might not just defy gravity, they could also vanish into thin air. You've probably heard of Hawking radiation, the eerie glow that causes black holes to slowly lose mass and evaporate over eons. But what if white holes do the same thing, just in reverse? Here's the twist. While black holes leak energy over unimaginable timescales, white holes might explode their energy outward in a dramatic finale. Imagine a black hole's life in rewind. Instead of fading away, a white hole could burst apart, releasing all its pent-up matter and radiation in one cosmic fireworks display. The math suggests this process would be staggeringly fast compared to a black hole's slow decay, lasting mere seconds before the white hole winks out of existence. But here's where it gets even weirder. If white holes evaporate, they'd unleash energy on a scale that dwarfs supernova. We're talking about temperatures hotter than the core of a star, packed into a fleeting, ultra-bright flash. Some theorists argue this could explain certain mysterious cosmic explosions, brief, violent events that leave no trace behind. Yet there's a catch. Hawking radiation relies on quantum effects near a black hole's edge, and white holes don't have an event horizon to trap particles the same way. So how would evaporation even work? One idea is that quantum gravity physics' biggest unsolved puzzle might rewrite the rules entirely, allowing white holes to dissolve in a way we can't yet predict. Whether they fizzle out quietly or go out with a bang, white holes keep pushing the boundaries of what we think is possible. Up next, we'll venture into even stranger territory. What if white holes aren't just cosmic oddities, but gateways to other universes? Now, let's stretch our imaginations even further. What if white holes aren't just cosmic quirks in our universe, but bridges to entirely different realities? This is where multiverse theories take center stage, painting a picture where white holes in one universe could be intimately linked to black holes in another. Picture this: a black hole in our universe sucks in matter, crushing it into oblivion. But instead of vanishing forever, that matter might erupt out of a white hole in a parallel universe, like water bursting through a cosmic faucet. This idea isn't just science fiction, it's rooted in the work of renowned physicist Roger Penrose, who proposed a mind-bending model called cyclical cosmology. In this framework, the death of one universe could seed the birth of another, with white holes acting as cosmic recycling centers. Here's how it might work. When a universe reaches its end, all its black holes could eventually evaporate via Hawking radiation, leaving behind a sea of energy. But according to Penrose, that energy might collapse into white holes, sparking a new Big Bang in a fresh universe. It's a never-ending cycle, universes dying and reborn, connected by these mysterious portals, but the implications get wilder. If white holes truly feed other universes, they could explain why our cosmos seems so finely tuned for life. Maybe the constants of physics like gravity or the speed of light aren't random at all, but inherited from a previous universe's white hole eruptions. It's a tantalizing thought, though one that's still purely theoretical. Of course, skeptics point out that we have no direct evidence for other universes, let alone white holes acting as interdimensional pipelines. Yet the math hints at possibilities beyond our current grasp, reminding us that the universe, or multiverse, might be far stranger than we ever imagined. Up next, we'll tackle another head-scratcher. What if white holes hold onto secrets that even black holes can't hide? Now, let's peel back another layer of cosmic mystery. What if white holes defy one of the most fundamental rules governing black holes? Enter the no-hair theorem, a principle suggesting black holes are shockingly simple. According to this idea, no matter what you toss into a black hole, whether it's a library of books or a spaceship, all that remains detectable from the outside are three basic traits: mass, electric charge, and spin. Everything else, from the object's composition to its history, seems erased. It's as if black holes have no hair, no extra details clinging to them. But white holes might flip this script entirely. Unlike their dark counterparts, white holes could theoretically retain far more information about what's ejected from them. Imagine a cosmic vault that doesn't just spew out random energy but carefully preserves the blueprint of what fell into a connected black hole. This throws a wrench into the no-hair theorem, suggesting that white holes might be the universe's way of keeping receipts. This ties directly into the fiery debate over the information paradox, a puzzle that's haunted physicists for decades. If black holes truly destroy information, it violates quantum mechanics, which insists information can never be lost. But if white holes act as cosmic archivists, storing and eventually releasing that information, they could solve the paradox in one elegant swoop. Some theorists even speculate that the chaotic bursts from white holes might not be random at all, but encoded messages from whatever fell into a black hole long ago. Of course, this is still speculative. Critics argue that if white holes do preserve information, we'd need a way to decode it, a cosmic Rosetta Stone we don't yet have. Plus, the no-hair theorem is deeply woven into our understanding of black holes, and challenging it isn't done lightly. But that's the thrill of white holes. They force us to question the rules we thought were set in stone. Up next, we'll dive into an even stranger possibility. What if white holes and quantum entanglement are playing a bizarre game together? Now, let's venture into one of the most mind-bending intersections of physics, where white holes meet the strange world of quantum entanglement. Picture this: two particles become entangled, their fates linked no matter how far apart they drift in the universe. Change one, and the other reacts instantly, defying the speed of light. It's a phenomenon Einstein famously called spooky action at a distance. But what happens when these entangled particles get close to a white hole? Theorists suggest the extreme gravity and energy near a white hole could twist quantum entanglement into something even weirder. Normally, entangled particles share a connection that's delicate but predictable. Near a white hole, though, that connection might stretch, warp, or even snap in ways we've never seen. Some models propose that the particles could become super entangled, responding not just to each other but to the white hole's violent outbursts, creating a three-way quantum dance. This isn't just cosmic spectacle, it could be a golden ticket to understanding quantum gravity. One of the biggest puzzles in physics is how to reconcile Einstein's theory of gravity with the bizarre rules of quantum mechanics. White holes, with their ability to warp spacetime and potentially alter quantum states, might offer a testing ground for theories like loop quantum gravity or string theory. Imagine detecting a pair of entangled particles near a white hole, only to find their behavior defies all textbooks. That anomaly could be the clue physicists need to crack the quantum gravity code. Of course, this is all speculative. White holes themselves are still theoretical, and testing quantum effects near one is, well, a challenge. But the idea highlights how white holes aren't just cosmic oddities. They could be keys to unlocking the universe's deepest secrets. Up next, we'll tackle another fiery debate. Do white holes have firewalls like their black hole cousins? And what would that mean for the laws of physics? Now, shifting gears to another heated debate in astrophysics, let's dive into the fiery mystery surrounding white holes. You've probably heard of black hole firewalls, theoretical walls of intense radiation that might incinerate anything crossing a black hole's event horizon. But could white holes have their own version of these blazing barriers? The idea of firewalls comes from a clash between quantum mechanics and Einstein's general relativity. For black holes, the firewall hypothesis suggests that instead of a smooth passage through the event horizon, there's a violent wall of energy, a last brutal test for anything falling in. Now flip that logic to white holes. If they're truly the time-reversed twins of black holes, shouldn't they eject matter and energy through a similar fiery exit? Some physicists argue yes, a white hole firewall would act like a cosmic bouncer, preventing anything from entering while violently expelling whatever's inside. Picture a star's worth of energy erupting outward in a searing blast, a spectacle that would make even supernova look tame. But here's the twist: relativity insists that passing through a white hole's event horizon should feel just as uneventful as drifting through empty space. Firewalls, by contrast, would shatter that principle, forcing physicists to rethink how gravity and quantum mechanics mesh at these extreme boundaries. Others push back, claiming firewalls are more mathematical quirks than physical realities. They argue that white holes, if they exist, might eject matter smoothly without the drama of a firewall. This camp leans on quantum corrections or alternative theories of gravity to resolve the paradox. The debate isn't just academic, it's a litmus test for our understanding of the universe's most extreme environments. If white holes do have firewalls, they'd challenge relativity's core tenets. If they don't, we'd need new physics to explain why. Either way, the answer could rewrite textbooks. Up next, we'll explore an unexpected cultural connection, how ancient myths might have eerily foreshadowed the concept of white holes long before modern science. Now, let's take a fascinating detour into the realm of ancient myths and legends. Long before telescopes or equations, cultures around the world described cosmic phenomena that bear an uncanny resemblance to white holes. Take the concept of the cosmic egg, found in creation stories from Hindu to Egyptian mythology. These myths speak of a primordial shell bursting open to release the universe, a striking parallel to how white holes theoretically expel matter and energy into space. The Hindu text Rigveda, for example, describes the universe emerging from a golden egg, while the ancient Egyptians revered the egg of the world as the source of all life. Even the Finnish epic Kalevala tells of a cosmic egg cracking to form the sky and earth. Could these stories be humanity's intuitive grasp of white holes? Some researchers argue yes, pointing out how these myths capture the essence of a sudden, explosive creation, much like a white hole's hypothetical outburst. But the connections don't stop there. The Dogon people of Mali, renowned for their advanced astronomical knowledge, spoke of a star that pours out matter, a description eerily similar to a white hole's behavior. Meanwhile, Greek philosophers like Anaxagoras theorized that the cosmos began from a single, dense point that expanded outward, an idea uncomfortably close to modern white hole theories. Skeptics dismiss these parallels as coincidence, but the consistency across cultures is hard to ignore. Whether these myths were poetic metaphors or genuine insights, they reflect a universal human curiosity about cosmic origins, one that science is still unraveling today. Next, we'll confront a sobering reality: why white holes might forever elude our telescopes despite their theoretical allure. Shifting our gaze from ancient myths to modern science, let's tackle a frustrating reality about white holes, why they might remain invisible to us no matter how hard we look. The core issue lies in their very nature. Unlike black holes, which pull everything in, white holes violently expel matter and energy in sudden, unpredictable bursts. These outbursts are incredibly brief, often lasting mere seconds or minutes, making them nearly impossible to catch with our current telescopes. Adding to the challenge is the extreme redshift effect. As white holes eject matter at tremendous speeds, the light they emit gets stretched to longer, weaker wavelengths, like a siren fading into the distance. By the time this light reaches us, it's often so faint and distorted that it blends into the cosmic background noise. Even our most advanced instruments, like the James Webb Space Telescope, struggle to pick up these ghostly signals. Then there's the energy problem. White holes are theorized to release energy in colossal, concentrated bursts. Think of a cosmic fire hose blasting matter outward. But without knowing when or where these eruptions might occur, astronomers are left scanning vast stretches of space, hoping to get lucky. It's like trying to photograph a lightning strike in a pitch-black storm. Some researchers suggest that certain gamma-ray bursts or unexplained radio flashes could be white hole activity, but these events are so rare and poorly understood that confirming a link is next to impossible. Until we develop technology capable of monitoring the entire sky in real time with ultra-sensitive detectors, white holes might stay just beyond our grasp. Yet, this very elusiveness fuels scientific curiosity. After all, the universe loves a good mystery, and white holes might be its ultimate cosmic hide-and-seek champions. Up next, we'll dive into an even stranger idea, that white holes could be popping in and out of existence at the smallest scales imaginable. Now, let's zoom way in, to the realm of the unimaginably small, where the fabric of space-time itself flickers with quantum activity. Here at the Planck scale, the universe behaves in ways that defy everyday logic, and white holes might just be part of the chaos. Picture this: empty space isn't truly empty. Instead, it's a seething ocean of virtual particles, constantly popping in and out of existence, borrowing energy from the vacuum itself. In this quantum frenzy, some theorists propose that microscopic white holes could appear and vanish in fleeting instants. These wouldn't be the colossal cosmic fountains we've imagined earlier, but tiny, ephemeral bursts of energy, more like quantum hiccups than stable objects. The idea hinges on the extreme conditions near the Planck length, where gravity and quantum mechanics collide, warping space-time into knots that could briefly resemble white holes. What's wild is that these quantum white holes might not even obey the usual rules of causality. They could erupt and disappear faster than the speed of light, leaving no trace behind, just a ripple in the quantum foam. Some models even suggest that these fleeting white holes could be entangled with microscopic black holes, creating a dizzying dance of creation and destruction at the smallest scales. But here's the catch: detecting such phenomena is, for now, pure science fiction. The energy scales involved are trillions of times beyond what our particle colliders can reach, and the events last for fractions of a second. Yet, the math hints that if we ever unlock the secrets of quantum gravity, we might find white holes hiding in plain sight, or rather, in the blur of the quantum world. This idea blurs the line between particle physics and cosmology, suggesting that white holes could be as fundamental to the universe as atoms, just far more elusive. Up next, we'll push the boundaries even further, imagining what it would take to harness a white hole's power, and why it might be the ultimate cosmic pipe dream. Now, let's take a leap into the realm of pure imagination where science meets science fiction. Picture an advanced civilization far beyond our current technology, attempting to harness the raw power of a white hole. The idea of a white hole engine sounds like something straight out of a cosmic fantasy, but it's a thought experiment that pushes the boundaries of what we understand about energy and physics. Think of a white hole as the ultimate cosmic battery, constantly spewing out matter and energy without any apparent input. In theory, if you could somehow capture and direct that outflow, you'd have an unimaginable power source. The energy output would be staggering, potentially enough to fuel entire civilizations for eons. Some calculations suggest that even a small white hole could release energy equivalent to billions of nuclear reactors operating at full capacity. But here's where reality crashes the party. First, white holes are hypothetical. We've never observed one, let alone figured out how to contain or control it. Second, the sheer intensity of their energy output would make them incredibly dangerous. The radiation and matter erupting from a white hole would likely vaporize any machinery or structure we could build today. And then there's the question of stability. White holes, if they exist at all, might be fleeting or unpredictable, making them useless as a reliable power source. Even if we could overcome these hurdles, the laws of physics as we know them might prevent such a feat. White holes defy entropy, and harnessing their energy could violate fundamental thermodynamic principles. For now, the white hole engine remains a fascinating but implausible dream, a reminder of how much we still have to learn about the universe's most extreme phenomena. Up next, we'll explore an even more mind-bending idea: how white holes might tie into the holographic principle, suggesting that our universe's information could be encoded on their surfaces. Now, let's shift our gaze to an idea that blurs the line between reality and something far stranger: the holographic principle. Imagine the universe as a cosmic projection, where all the information we see in 3 dimensions is actually encoded on a 2-dimensional surface. It sounds like science fiction, but this mind-bending concept might extend to white holes too. Think of a white hole's surface as a kind of cosmic hard drive, storing information about everything it ejects. Just like a hologram where a flat image creates the illusion of depth, a white hole could hold all the data of the matter and energy it releases on its boundary. This ties back to the holographic principle, which suggests that our entire universe might work the same way, with all its complexity reduced to information painted on a distant, invisible surface. But why does this matter? If white holes do encode information on their surfaces, it could solve one of physics' biggest puzzles, the black hole information paradox. Black holes seem to destroy information, which clashes with quantum mechanics. But if a black hole transforms into a white hole over time, as some theories suggest, that information might not be lost after all. Instead, it could be preserved on the white hole's surface like a cosmic backup. Of course, this is all speculative. We don't yet have the tools to test whether white holes or the holographic principle are real. But the idea itself opens doors to wild possibilities. Could our universe be a hologram? Are white holes the key to understanding how information flows in the cosmos? For now, these questions remain open, teasing us with glimpses of a deeper truth hidden in the fabric of reality. Up next, we'll dive into an even more intriguing twist: the idea that black holes and white holes might not be so different after all, but two sides of the same cosmic coin. Now, let's explore a fascinating twist in the cosmic tale: the idea that black holes and white holes might be two phases of the same celestial object. Picture a black hole, that relentless devourer of matter, slowly transforming over unimaginable timescales into its opposite, a white hole bursting energy back into the universe. This isn't just science fiction. Some theories in quantum gravity suggest that when a black hole reaches the end of its life, it doesn't just vanish. Instead, it could undergo a dramatic metamorphosis, flipping into a white hole. The key to this lies in the strange rules of quantum mechanics. At the tiniest scales, particles can tunnel through barriers they shouldn't classically overcome. Apply this to a black hole's collapse, and you get a wild possibility: quantum effects might allow the black hole's singularity to rebound, creating a white hole. This process would take an incredibly long time, far longer than the current age of the universe, but mathematically, it's not impossible. What's even more mind-bending is how this could solve some of physics' biggest headaches. Remember the black hole information paradox. If a black hole becomes a white hole, the information it once swallowed isn't lost forever. It's just stored until the white hole releases it. This could mean the universe has a built-in recycling program for information, preserving the rules of quantum mechanics even in the most extreme environments. Of course, there are hurdles. For one, we've never observed a white hole, let alone caught a black hole in the act of transforming. And the timescales involved are so vast that testing this idea directly seems impossible. But that's where theoretical physics shines. It lets us ask, what if? And follow the math wherever it leads, even to places as strange as a black hole's rebirth. So, could every black hole in the universe secretly be a white hole in waiting? The answer, for now, is hidden in the quantum fog. But the very possibility reshapes how we think about these cosmic extremes, not as separate monsters, but as two faces of the same mysterious phenomenon. Coming up next, we'll venture into the realm of string theory, where extra dimensions might hold the secret to stable white holes and a whole new layer of cosmic weirdness. Now, let's take a leap into the world of string theory, where the rules of the cosmos get even stranger. Here, the idea of white holes takes on a whole new dimension, literally. While classical relativity paints white holes as unstable, fleeting bursts of energy, string theory suggests they might have a way to stick around, thanks to the hidden fabric of the universe. String theory proposes that reality isn't just the 3 dimensions we experience, but up to 10 or 11, all curled up in ways too tiny for us to notice. In this framework, white holes could find stability by anchoring themselves in these extra dimensions. Imagine a white hole not just as a cosmic geyser in our familiar space, but as an object whose roots stretch into unseen layers of reality. This could explain why we've never spotted one. They might be hiding in plain sight, tied to dimensions we can't yet probe. What's fascinating is how this clashes with Einstein's classical view. In general relativity, white holes are like unstable bubbles doomed to pop almost instantly. But string theory's extra dimensions could act like cosmic scaffolding, propping them up long enough to leave a detectable mark. Some models even suggest that these higher dimensional white holes could be gateways connecting distant parts of the universe, or even other universes in ways that defy our everyday intuition. Of course, this is all theoretical. String theory itself remains unproven, and the math behind these ideas is fiendishly complex. But if extra dimensions do exist, they might rewrite the book on white holes, turning them from cosmic mayflies into enduring fixtures of the multiverse. Up next, we'll explore an even more tantalizing idea, that certain gravitational wave patterns could be echoes of white holes, hinting at their presence in the universe's symphony. Now, let's turn our attention to something even more mysterious, the whispers of white holes hidden in the fabric of space itself. Scientists have long wondered if these cosmic oddities leave behind any trace, and recent discoveries suggest they might be sending us faint echoes through gravitational waves. When the Laser Interferometer Gravitational Wave Observatory, or LIGO, first detected ripples in space-time from colliding black holes, it opened a new window into the universe. But some of the signals it picked up didn't quite fit the expected patterns. Among these anomalies were faint, repeating echoes, tiny ripples that arrived just after the main gravitational wave event. Some researchers believe these could be the fingerprints of white holes reverberating long after their explosive birth. Here's how it might work. Imagine a black hole collapsing, but instead of vanishing into a singularity, quantum effects cause it to rebound as a white hole. The transition would send out a burst of energy, a gravitational shockwave followed by smaller, delayed echoes as space-time settles. These echoes would be subtle, like hearing a distant shout bounce off a canyon wall. If LIGO odd detections are indeed these echoes, it could mean white holes aren't just theoretical, they're out there, leaving ghostly traces in the data. Of course, not everyone is convinced. Critics argue these echoes could be noise or artifacts in the detectors. But if future observations confirm them, it would revolutionize our understanding of gravity, quantum physics, and the life cycle of black holes. Up next, we'll dive into an even stranger idea, white holes entangled with theoretical time crystals, where the very fabric of reality might behave in ways that defy our expectations. Now, let's venture into one of the most mind-bending intersections in theoretical physics, where white holes meet the bizarre world of time crystals. If you thought white holes were strange on their own, wait until you see how they might interact with these exotic structures that seem to defy the very nature of time itself. Time crystals are a relatively new concept, first proposed in 2012 by Nobel laureate Frank Wilczek. Unlike ordinary crystals, which have repeating patterns in space, time crystals exhibit repeating patterns in time. Imagine a clock that ticks forever without any energy input, a perpetual motion machine but on a quantum scale. Now pair that with a white hole, an object that violently ejects matter and energy without any apparent source. The combination could create something even wilder. Near the boundary of a white hole, the extreme gravitational forces might distort space-time so severely that it could stabilize a time crystal's oscillations. Think of it like a pendulum swinging endlessly in the turbulent winds of a white hole's energy outflow, never slowing down. Some theorists suggest this could create a feedback loop, where the white hole's energy sustains the time crystal, and the time crystal's rhythmic structure influences how the white hole emits matter. But here's where it gets even weirder. If time crystals near white holes truly exist, they might allow for perpetual motion, not in the impossible energy-creating sense, but as a natural consequence of quantum mechanics in these extreme environments. This could challenge our understanding of thermodynamics, entropy, and even causality, since time crystals inherently break time symmetry, meaning they don't behave the same way if you reverse the clock. Of course, this is all speculative. No one has observed a time crystal in space, let alone near a white hole. Yet the mere possibility opens doors to unimaginable phenomena, like space-time itself behaving like a never-ending dance of energy and structure. Up next, we'll tackle an even more pressing question: what happens if humans try to create white holes themselves, and whether doing so could unravel the fabric of reality. Now, let's shift our focus to a question that sounds like it's straight out of science fiction, but could one day become a very real scientific challenge. What if we could create white holes ourselves, not in the depths of space, but right here on Earth? The idea isn't as far-fetched as it might seem. Some theories suggest that under extreme conditions, like those inside powerful particle colliders, microscopic white holes could briefly form. These wouldn't be the cosmic monsters we've been discussing. They'd be tiny, fleeting, and likely vanish almost instantly. But even the possibility raises serious ethical questions. Imagine a scenario where a particle collision accidentally creates a stable microscopic white hole. Unlike black holes, which swallow everything around them, a white hole would violently expel energy and matter. If it didn't evaporate immediately, it could unleash an uncontrollable burst of radiation, potentially damaging equipment or even posing a risk to nearby researchers. Then there's the doomsday scenario. What if such a white hole grew instead of disappearing? In theory, it could start ejecting matter at an accelerating rate, leading to a catastrophic energy release. While most physicists dismiss this as wildly improbable given how quantum mechanics and Hawking radiation would likely prevent it, the mere possibility has sparked debates about the limits of human experimentation. This isn't just hypothetical. Similar concerns were raised when the Large Hadron Collider first powered up, with some fearing it might create Earth-devouring black holes. Those fears were unfounded, but they highlight a real tension. How far should we push the boundaries of physics when the consequences are unknown? For now, artificial white holes remain firmly in the realm of theory. But as colliders grow more powerful and as quantum gravity research advances, the line between science fiction and science fact might blur. The question isn't just whether we can create white holes, it's whether we should. Coming up next, we'll explore an even more mysterious idea. Could white holes act as cosmic sensors, hiding the universe's deepest secrets from us? Now, let's turn to an idea that sounds almost poetic: white holes as cosmic sensors, hiding the universe's most extreme secrets from view. This ties into something called the cosmic censorship conjecture, a principle proposed by physicist Roger Penrose. The idea is simple yet profound. The universe might have a way of shielding us from the chaotic, unpredictable heart of singularities, those infinitely dense points at the core of black holes, and possibly white holes too. Think of it like this: singularities break the rules of physics as we know them. Gravity becomes infinite, space-time curves beyond recognition, and our equations just stop working. If these cosmic monsters were exposed, they'd make the universe fundamentally unpredictable. But what if nature has a built-in safety mechanism? That's where cosmic censorship comes in. It suggests that singularities are always hidden behind event horizons, the invisible barriers that prevent us from seeing the chaos within. Now apply this to white holes. If they're the time-reversed twins of black holes, do they also hide singularities? Some theories say yes. A white hole singularity could be tucked away, spewing out matter and energy without ever revealing its unstable core. This would preserve the universe's order, ensuring that physics stays reliable even in the face of these bizarre objects. But here's the twist: not all physicists agree. Some argue that white holes, especially if they form from quantum effects, might not play by the same rules. Could their singularities ever be naked, exposed for the universe to see? If so, it would challenge cosmic censorship and force us to rethink how space-time behaves at its most extreme. For now, the debate rages on. But one thing's clear: white holes, whether as cosmic sensors or rule breakers, push our understanding of reality to the limit. And that brings us to our final discovery, where we'll ask the biggest question of all. What's the ultimate fate of these enigmatic objects? Now, let's venture into the grand finale of our cosmic journey, the ultimate fate of white holes. What happens to these mysterious objects in the far, far future? Do they vanish, collide, or even open doorways to entirely new realms? The theories here are as wild as they are fascinating, stretching the limits of our imagination. One possibility is that white holes simply fade away. Just as black holes slowly evaporate through Hawking radiation, some physicists suggest white holes might dissipate over unimaginable timescales, their energy scattering into the cosmos until nothing remains. But here's the twist: because white holes are time-reversed black holes, their evaporation could look like a black hole forming in reverse, a bizarre cosmic rewinding of events. Then there's the idea of mergers. If white holes exist, could they collide with black holes or even each other? The math gets messy here, but some models hint at explosive interactions where the two objects might annihilate each other in a burst of energy or create something entirely new, a hybrid object defying our current understanding. But the wildest theories take us beyond our universe. Imagine white holes as bridges to other dimensions or parallel realities. In some multiverse models, a white hole in our cosmos could be linked to a black hole in another, funneling matter and energy across the fabric of existence itself. This ties into cyclical cosmology, where universes are born from white holes and die as black holes, an endless loop of creation and destruction. Of course, these ideas are speculative, pushing the boundaries of known physics. Yet that's what makes white holes so thrilling. They force us to ask questions we don't yet have answers to. Whether they vanish, merge, or transcend, one thing's certain: white holes remind us that the universe is far stranger and more wonderful than we've ever imagined. And with that, we've reached the end of our exploration. From cosmic sensors to multiverse gateways, white holes challenge everything we thought we knew. Who knows what future discoveries might reveal? Until then, keep looking up and never stop wondering. If you enjoyed this journey through the weird and wonderful world of white holes, don't forget to like, subscribe, and hit that notification bell so you never miss out on the next cosmic mystery. Thanks for watching, and as always, stay curious. As we wrap up this mind-bending journey through the mysteries of white holes, let's take a moment to reflect on just how much these cosmic oddities have reshaped our understanding of the universe. From their bizarre time-reversed nature to their potential role as gateways to other dimensions, each discovery we've explored today pushes the boundaries of physics in ways that even Einstein might find astonishing. Think about it: white holes challenge the very laws we thought were set in stone. They defy entropy, flirt with the origins of the Big Bang, and might even hold the key to unraveling dark matter. They've inspired scientists to rethink everything from quantum gravity to the holographic principle, proving that the cosmos still has plenty of surprises up its sleeve. And while we may not have all the answers yet, that's the beauty of science. Every unanswered question is an invitation to explore further, to peer deeper into the cosmos with next-generation telescopes and bold new theories. Who knows, the next great breakthrough about white holes could be just around the corner, waiting for someone like you to piece it together. So, what's your take on these cosmic enigmas? Do you think white holes are lurking out there, or are they purely mathematical curiosities? Drop your thoughts in the comments below. I'd love to hear which of these 25 discoveries blew your mind the most. And if you enjoyed this deep dive into the unknown, don't forget to like, subscribe, and hit that notification bell so you never miss out on our next adventure into the wonders of space. Thanks for joining me on this journey, and remember, the universe is always stranger than we imagine. Keep looking up and stay curious.